Hi everybody. I'm Steven Kolawole, and it's so great to be here today. Yeah. I'll be speaking on my project, which also later became a paper, and it's about sign to speech modeling for sign language understanding, focusing on the on Nigerian sign language. Right. Okay. Here's a little background about the project. So it started off as a fun project, I mean, as an end-to-end working prototype that detects sign language meanings in images and videos and generates the equivalent voice of words that is being communicated by the sign language. And it's doing all this in real time, right? Yeah. So initially, I created the data set using my webcam. I learned I learned about nine sign words online, and then I used that um, to create my data set. So, and then I had this working prototype right? And then when I was done with that, I it was submitted to a challenge on Twitter. I think it's an AI challenge hosted by DeepQuest, and I won the challenge with this. So a friend of mine, Okoyemi Oshakwade, she works as a researcher, as a machine learning researcher at Data Science Nigeria. So we got talking about the project, and then I asked, is this project the sort of project that could be scaled up, for research? Then I was thinking of, transiting into machine learning research for my, stable machine learning engineering role. So I talked to her about it, and she was like, "Oh, sure, yes, we can do this." And yeah, so we started thinking about making this a research project. And yeah, so that leads to me conversing with my career mentor, uh, Dr. Babatunde Olorishade. And she is currently a senior lecturer of data science and software engineering at Cardiff Metropolitan University. So I had a chat with him alongside Okoyemi, and then we decided we decided the scope of the project. I mean, how much how far do we want the project to go? I mean, what should we be targeting, right? So we started doing literature review, trying to see existing works in that particular field. I mean, the sign to speech domain, right? So we did that, and during the course of the literature review, we got to realize that even though sub-Saharan Africa is like the region with the largest number of cases for hearing impaired community, and but it's also the community, it's also the region with the lowest number of solutions targeted towards solving this, right? So that was when we started thinking. That was when we started thinking about about solution design, and then got to realize that okay, there's no there's no usable or producible data sets out there right now for any of the sub-Saharan Africa country, right? So if we're trying to solve this problem in the sub-Saharan African space, then we need to create our own data sets, and then I mean, we need to create a tuner data set, and uh, we need to perform lots of computationally expensive experiments and likes. So that was when I got to join ML Collective. So ML Collective is like an open lab for machine learning researchers. So let's say you're just getting into ML research, or you're already a researcher in the field, but you just want to be engaged with the community beyond your work, beyond your workspace or your lab. Then ML Collective is like the right place to be at. So the ML Collective was having this research jam, and I told them about my project and how I'm thinking of scaling it up into a research project, to solve a bigger problem. And then, yeah, I got a lot of very enthusiastic feedbacks, and they those really, gave me courage to pursue this as a research project. And later on, ML Collective gave me the compute resources to scale up my project, right? Yeah. And then in the final stage of the project, I met Naya Saxena to ML Collective. So Naya Saxena is currently a final year student at University of Toronto. She is an accomplished researcher already. I think he has about several publications already, even though he's an undergrad. Yeah, so he mostly helps with the with you know expansive literature review, just to be sure that we're covering all the blocks, right? And then with the paper writing, I was new to LaTeX, I was new to academic writing generally, and Nayan was a very big help in that regards. All right, so in the end, we had this ready, this particular paper, and it got into a paper. It got into a workshop at New Whips. So if you're not familiar with New Whips is like the most prestigious machine learning conference right now in the world. And yeah, so the paper managing to get into the workshop at NEWIP's ML4D, uh, machine learning for developing world workshop at NEWIP's, was really a big moment for me, considering that this was my first research endeavor and all. So yeah. All right, so in this talk, I would go through the background, which I've already covered to a good extent, and then I'll talk about the data sets, I'll talk about the experiments, the evaluation, and the subsequent deployments, and finally, I'm going to show us a live demo. Yeah. All right, so considering the background, usually if one is pursuing a research project, then you need a motivation. You need to be, solving a particular problem, right? And then yeah, the motivation for this was to reduce the communication barrier between the hearing impaired community and the larger, society. They focus on sub-Saharan Africa, and this is the region with most cases of hearing disabilities. And the way we're proposing to do this is by developing a lightweight science-to-speech solution that works in real time. The fact that I'm from Sub-Saharan Africa, I think that makes it a no-brainer for me. So, yeah, so during our research, we discovered that the lack of solutions for this problem in Sub-Saharan Africa is mostly due to two factors. The first one is that sign language data in the region is extremely low resource, right? So when we're doing our study, we realized that only two sign language data sets exist how in the sub-Saharan Africa space. And one is a South African sign language data set, and the other is a Ghanaian sign language data set. And it turned out that both data sets are just POC, proof of concepts. I mean, it's not really something that you could use for reproducible science. So we needed to create one from scratch if we want to, circumvent this particular problem. And the second issue is that the increasing complexities and advanced tools required to deploy the solutions in real-time environments, in real-life environments. For example, there's this use of kinetic loss, right? And then, yeah, that's quite a high level of complexity in that particular solution. And what we want is something that can be easily deployable, something that can be made use of very easily with very little computational expenses and financial constraints. So yeah. So all right. So considering our approach, the first step was to create a novel data set for a sub-Saharan sub-Saharan African country, right? And then since I'm a Nigerian, it makes sense to start with the Nigerian Sign Language. And then secondly, we plan to, do different experiments. We plan to, carry out different scientific test experiments with, several models. More on that later. And then finally, we plan on deploying the best performing model for real-time usage while converting the sign the return sign words to speech. All right, so concerning the data set, over 8,000 images were created, and then we did this by soliciting the help of a TV side language broadcaster. I wrote to the local TV broadcasting corporation in my state. Yeah. And then I was opportune to get a TV sign language broadcaster, Amanda. And she was very helpful in creating the first batch of the data set. And the second batch was created via, collaborations um, with special education teachers and, the special education students from two schools in Nigeria, right? And yeah, in the end, this is what we had. We had a widely dispersed data set of 20 individuals captured in diverse backgrounds and lighting conditions, right? If you look at this, you see that the backgrounds are quite diverse. We try to account for low lighting, and then we try to account for a little bit of blurs in the images. Yeah, so what we were just trying to do is to make sure that this model could perform very well in the wild, right? It can generalize to previous unseen environments and backgrounds. And yeah, so while carrying out the data preprocessing and annotation, this is the data set to 5,000 images. Right? Yeah. So and then we made use of label IMG to annotate the images for update detection in both TXT and XML formats. All right. So considering the experiments and the evaluations, so we tried out different models. The first one is the YOLO V5 model. YOLO V5 model is a very well-known object detection model out there. And then we tried out an SSD model using ResNet 50 FPN. ResNet 50 is a very popular object detection model too. And then finally, we discarded the annotations the annotation files, and we use just the images to train a plain classification model. And we made use of mobile note tool as our classification model. All right, so for the YOLO model, we made use of the text format annotations, and then we tried out different data augmentation techniques, including HSV manipulations. HSV simply means hue saturation values. These are light settings. Yeah, I'm not sure if you've tried to edit an image before or a photo before on your mobile phone, and then yeah, you could edit the hue, the saturation. You could or play around with all these lighting conditions, right? Yeah. That's the same thing that the issues with manipulations did. And then we tried scaling, zooming in and out, and we tried the left, right flipping, flipping it this way and flipping it that way, and just trying to see if the model can blend with all the little perturbations to the images. And then we trained over 150 epochs in batch size of 16. Yeah, this is our model performance over time. Yeah, I think these are the most important. This five right here are the most important metrics. Yeah, so you can see that the classification is the classification. Oh, sorry, the precision score it was increased over time, up to I think 0 point with a little bit over 80%. The same as the record. The record score is almost close to 100%, right? And then we have the mean average precision map at 0.5. Let me explain map in a bit. So map mean average precision at IOU 0.5 is simply the IOU means the intersection over union. So we we have this boundary box over the we have the two boundary box that we annotated over that sign box, and then our model is trying to predict an equivalent boundary box, right? So the intersection over union, is simply the overlap between the true boundary box and the predicted boundary box, right? and this particular one is at 50% overlap. So we try to gauge if the we try to gauge the accuracy of the boundary boxes overlap at 50%. Yeah, we have something close to 100% over here. And then when we try to compare it at 95% overlap, we have something close to say 70% accuracy. All right, so moving on. So for the single shot detector model, we made use of TensorFlow. Yeah, I should mention that the YOLO V5 model was 20 using PyTorch. Yeah. So for the SSD model, we made use of TensorFlow object detection API to be precise, and we use that to access and fine tune the SSD ResNet 50 model. Yeah. So the Western 50 model was already trained on the COCO 2017 dataset. It's a very popular dataset out there for object detection. And then the image and annotations were converted to T5 record formats. Anytime you're building a model via TensorFlow object detection API, you need to convert your files, your working files to TF record format. Yeah. So in terms of data augmentation, we only made use of horizontal flipping, and we try to use cropping, right? And then we trained across 40,000 training steps. So for the final model, the MobileNet V2 model, we made use of MobileNet V2 as a classifier while we discarded the annotations, and then we initially we trained over 60 epochs, right, using just feature extraction only, right? So we try to we trained the thing with feature extraction is we are not retraining any of the layers of the MobileNet V2. We're only putting a dense layer on top of the MobileNet V2, and then the dense layer is the is the one classifying it into our different classes. Yeah. Yeah. So we're not retraining any of the layers. We're just making use of the MobileNet V2 as our feature extractor. And then secondly, and then in the next step, because the first the feature extractor approach wasn't working too well, so we trained across 150 140 epochs, and then we fine-tuned the MobileNet V2 as 152 layers. So we retrained the top 52 layers, right? We fine-tuned them, and then we trained across 140 epochs of training. And then in the end, this is our model performance, comparing the feature extraction to the fine-tuning approach. Yeah. So the green line, the horizontal green line is the vertical green line is what's the name? Is the point where we start fine tuning, right? And you can see here that the loss, the loss is over the chart. Or why trying out? I mean, why using why doing the feature extraction approach? But um, when we started fine tuning, you could see that the loss, really came down, right? To around 0.1 or 0.1 point. Yeah. So looking at the accuracy, we could see that there's a sort of a linear approach, there's a linear progression over time in the accuracy. So maybe the fine tuning didn't really help in terms of accuracy. Yeah. But while also looking at precision, we could see that the precision score also was crazy, right? Before we made use of not really crazy per se, but yeah, it wasn't. I guess the trying to fine tune on the precision, trying to fine tune on the fine tune the model. The precision score is a little bit redundant in that regard. But looking at recall, we could see that the recall score skyrocketed immediately we apply the fine tuning approach. All right, so here's the final evaluation. So we have our YOLO model performing the best, and the classification model wasn't too far behind. Yeah. So we could say that in recall, YOLO was performing the best, and then in precision, we have mighty we have a what's the name? We have a classification performing the best with almost 91% accuracy. And then for the mean average precision at IOU 0.5, the SSD model performed well. But I was thinking maybe it's overfitting, yeah, because his recall and precision score wasn't too good. So yeah, this particular score was a little bit questionable, right? Yeah. So in the 0.95 overlap, we have the YOLO model performing better than this, but the difference is just marginal, right? So I guess most times I'll probably trust the result of the YOLO model to the SSD model. All right. So afterwards, the return scientists were converted to speech using a Python library known as PyTXT. So PyTXT is a text to audio conversion library. Yeah, it's very easy to use, no stress at all. Yeah, and then finally we deployed the model on the DeepStack server, right? Using Docker, and that means you could the link to the GitHub repository is at the end of this slide. So if you want to try it out, yeah, you could. All you just need to do is to install Docker on your laptop, and then maybe install DeepStack via the if you're using Ubuntu or any of the Linux machines, you could install DeepStack via Docker, using the CLI approach. But if you're on Windows, then you need to download the executable file to install it. Okay, so here's the demo. So concerning the demo, I have the model. I have the model server spinning up right here. It's a Docker file. I mean, this is the DeepStack server, and yeah. And over here, I have the live feed detection running over here, and it's going to open up my webcam and detect video live, detect the sign live. So see this, and so there's nothing right now. Okay, you can hear that, right? So I'm trying to capture the alphabets.
B.
That's B.
B. C. C.
That's
C.
then
C.
you could see it's
D.
sending the
D.
request to the endpoint
D.
over here. I mean,
F.
sending
F.
the request as
F.
API endpoints to the DeepStack server over here. And right now, I'm trying to use it to form a sentence.
I am take. Sorry.
Okay, yeah.
Sorry.
So I just use it to form.
Sorry.
I am sorry.
Sorry.
All right. Okay. So one thing I want us to note here is one. I wasn't part of the dataset creation. I wasn't part of the dataset creation. I'm not talented enough when it comes to sign languages. Yeah. So I wasn't part of the sign language design dataset creation. So and also looking at this background, this particular background has not been shown to the model before. I mean, we didn't capture any of the data in a background that is similar to this. And I'm not sure if you can see the light over here. The light over here, its purpose was to distort the image, the signs that I'm trying to perform, right? So that it's not too clear, it's not too obvious to the model. And then despite all the constraints that I try to set for this model, just to see how well it could generalize, how well it could perform in the wild. I think it performed extremely well, like brilliantly. I mean, it was able to capture most of my words with it's very good accuracy. I mean, very strong accuracy. Yeah. Okay, so having said that, let me move on to the challenges, some of the roadblocks that we encountered while working on this project. So the first one is dataset creation. Believe me, that was hectic. Yeah, it's not an experience I really want to go through again. Yeah, so because the dataset creation, I had to book appointments, and the TV sign language, the TV broadcasting corporation I reached out to, they were ignoring me at first. Yeah, I don't know, probably because of students. I'm a student, or I don't know why, but yeah, they weren't very promising initially, but I just had to, persistent and, being a pain in the ass for them, and before they, before they eventually got back to me. And yeah, and Amanda was very sweet with the whole data separation. Um, but by the time I was reaching out to the sign language, to the special education schools, I already have a proof of concept. Yeah, so all I just need to do was to go to the school to show them my demo, you understand, my prototype, and show them how it works. And they were very, very enthusiastic about the project, and yeah, they agreed very easily with the whole data set creation. Okay, so but nevertheless, I mean, while I was, I had to use my local machine for the whole data set creation. I borrowed, I mean, when I went to the special education schools, I borrowed three laptops, for my friends, and just set them up while having the students and teachers perform in front of the webcam. Yeah, so the data annotation was even more hectic. If you remember me saying that we had 8,000 images created, and we had to annotate each and every one of them by hand. Yeah, I did that anyways, but it was crazy, right? And it's not really an experience I really want to, go to again. Yeah. All right. So another roadblocks when we submitted the paper to NEWIPS. So the one of the reviewers mentioned that how do we plan to secure the signer's identity, right? I mean, some of them might not be enthusiastic about having their faces in the open, right? So, and then in all my discussions with my dataset creators, I although I let them know that I was going to release the work publicly, and yeah, I might have to release the dataset publicly, but I only had a verbal agreement with them. I mean, a handshake agreement. And then, if I'm putting out the data set in the out in the I mean in the public, I I mean they need to be very aware of that particular action, and I mean they need to be aware of the implications and if they are cool with it, right? And if verbal agreement doesn't cut that, so I need to have a written agreement with them, concerning that. And so far I've been occupied with other stuff, with grad schools and work commitments. So I've not really had the time yet to go back and have the data set really sorted out. So yeah, it's still pending decision for now. All right. So I'm using this medium to say thank you to Emo Collective for the computational resources. Initially, I was training. I was training on Google Colab. If you're familiar with Google Colab, then you know that on Google Colab you have a cap on the amount of GPU or TPU that you could use, and also there's a limit. What's the name? It's an interactive ID. It's an interactive development environment. So you cannot leave your model training and go on to something else. You have to stay right there. I mean, if your screen is idle for like 20 minutes or so, you're going to get a prompt message if you stay there, and so that means I remember the first training I did, I had to sit in front of my laptop, on Google Colab for 13 hours straight up. Yeah. I mean, I had to stay and watch my models. Believe me, that was very crazy. So I told the Emo Collective people about it, and I was given computational resources, to get my work done. So yeah, I started using GPU. I started using Google Cloud Platform afterwards. Yeah. So if any one of you is looking at going into research, or you need a research body, you need a research help, you need anything concerning to research, I feel ML Collective is a very good place to be at. All right, so thank you very much for taking your time to listen to my talk. And if you want to try out the code, if you want to have a look at the code, or you just want to try out the model, the same model, yeah, go to this link. I have the link right here, so you could always try out the model if you want to try it out. If you have any objections, yeah, if you have any issues, feel free to, put an issue on the GitHub page, and I'll be, very enthusiastic to to clarify anything, or just work with or your questions and comments. And yeah, so I have the print of the paper on archive. So if you want to check that out, so check that. I might submit that to to a as a full conference paper, I mean, sometime soon. Yeah, but right now I'm not speaking on it. All right, so thank you, and I'm done with the presentation.